All right, let's take a look at rotational motion. So rotational motion is going to bring in a whole new set of variables for us. So we're going to have theta, omega, alpha. These are going to be our new variables, and we need to relate them to our old variables, our linear ones. Now we can relate those by saying that the distance traveled is equal to theta times r. So let's see what that looks like in more of a pictorial sense. So I have theta here, which is defined as arc length divided by radius. So I can go ahead and define what our theta is in terms of arc length and radius. And the arc length is the distance traveled, so that's how we're going to relate it to our linear situation. Now something's a little different. In the past, we've always done straight line motion. Now we're taking it along the path on this outside edge of the circle. So just kind of keep that in mind when setting up and solving these problems. Okay. We also see that we can relate the linear speed to the angular speed and the linear acceleration to the angular acceleration. Now notice I put this little subscript here on the tangential acceleration. So we're going to add in some new terms as well. So we have things like angular displacement, or the angle through which it travels. We have the angular velocity, or the rotational velocity, or the angular speed, or the rotational speed. And now we're going to talk about this not just as speed, but we're also going to call it the tangential speed. And the reason for that is the tangential speed, the speed of any point moving around here, its direction of that velocity is always going to be tangent to the circle. And then lastly, we have the acceleration. We have this a tan. And so what we're going to do is we're going to break a tan, or the acceleration I should say, into two parts, a tan and AC, or a rad, depending on what kind of variable you're using. So the radial acceleration, or the centripetal acceleration, is always pointing inward. And this is what's causing the change in direction as you go around the circle. A tan, this is always tangent to the circle, and this is always changing the magnitude of your velocity. So we're changing the direction of the velocity, and we're changing the magnitude of velocity. So we've kind of broken into components that way. So a tan is always going to be speeding up or slowing down, where AC is just, it's going in a circle. So a tan is going to correspond to the angular acceleration. Is it speeding up or slowing down angularly? Okay. AC, we do have a couple equations we can write for AC. So AC is going to be either V squared over R or omega squared times R. Depending on which situation you're in, am I dealing with linear quantities or angular quantities, you can pick which one to use there. Now when it comes to the equations, okay, so when we get to the equations, our equations are going to be the same because the relationship between angular displacement, angular velocity, and angular acceleration are the same relationships. They're defined the same way, that like velocity is a rate of change of position, angular velocity is a rate of change of angular position. So we've defined them the same way, so our equations come out the same. We just have to translate them into the new variables. So wherever you see a V, you would write an omega, and wherever you see V naught, it'd be omega naught plus 2a, and instead of a, we're going to have alpha, and instead of x, we're going to have theta. So I have theta minus theta naught. And so all the equations are going to come out similar. What this means for us is when we solve one of these problems, we are going to just list our variables, pick an equation, solve. Very similar to how we did it before. So let's try one of these. So what I have here for us today is I have the centrifuge, so it kind of spins like this. And in there are some vials. And so you could place, say, a test tube in there if you wanted to separate the materials in there. So I looked up the specs on this, and it turns out that the point that's at the very end here is 13 centimeters from the axis of rotation to that point. So I've identified the radius as 13 centimeters, and I know that this thing is rotating at, well, it can speed up to 3,200 RPM. That is not the maximum. That was just the test I did. It was 3,200 RPM, and it made it there in 100 seconds. So it took a little bit of time to get up to that speed. So what we want to do is we want to say, okay, What was the angular acceleration during that 100 seconds to get it up to that 3,200 RPM? How fast is that point going linearly? Very similar to how fast is this point on the outside edge moving as it spins up to speed. And then lastly, we want to figure out what the AC value is. And we're actually going to put that in G's of acceleration so we can figure out how much kind of G force is acting on those points at the outside edge, causing that separation, which is the main focus of what a centrifuge does. All right, so to start with, we have that 3,200 RPM. Now, RPM, you might want to say radians per minute, but it actually stands for revolutions per minute. So the first thing we're going to have to do is convert that, because we want these things in radians, radians per second, and radians per second squared. Okay, so I'm going to rewrite this as 3,200 revolutions per minute. And I'm going to convert this to radians per second. So I have revolutions, I'm getting rid of revolutions, I'm going to radians, there's 2 pi radians in 1 revolution. I have minutes on the bottom, so to get rid of it, I need to put it on top. And there's 60 seconds in a minute. This will be my angular velocity after that 100 seconds. So it took 100 seconds to go from rest, radians per second, up to this 3,200. I typed that in my calculator already. It's about 335 radians per second. And it doesn't tell me where it starts, so I'm just going to choose that as 0. Now that I'm down to 2 unknowns, I should be able to solve for alpha. Now to pick what equation I'm going to pick one without theta. So that would be my equation number 1. So I have omega equals omega naught plus alpha t. Crossing out, that is 0, and solve. So my alpha is my omega divided by t, so my 335 divided by 100 gives me 3.35 radians per second squared. There. Okay, so that is the angular acceleration. So every second it is speeding up by 3.35 radians per second. And it does that for 100 seconds, at which point it reaches that 3,200. Now to figure out the linear speed, so I'm trying to find the linear speed, I need to know the omega and the r. Okay, so I just found the omega a second ago, so v is equal to omega times r. So v is going to be that 335 times that radius of 0.13. And so when I typed that on my calculator, I ended up with a speed of 43.6 radians per second. That is, meters per second, I was right there. Meters per second. So I had that 43.6 meters per second. This is approximately, gosh, it was real close to 100. What was it? 97 miles an hour is how fast that point is moving around on here. And that isn't even at the maximum speed of this centrifuge. It does start to walk a little bit on you once you get up to those speeds. All right, and then the last thing I want to do is I want to figure out the centripetal acceleration. So AC is v squared over r. Go ahead, plug that number in along with your radius of 0.13. And I got a huge number. I got 73,079 meters per second squared. And if I divide that number by 9.8 to get it into G's, that's 7,457 G's of acceleration. That is a huge amount of G-force on those particles. And so as a result, it causes those heavier ones that have to apply a bigger force to go in a circle to get pushed out further because there's not enough force holding them there, and the lighter things that require a smaller force to kind of come to the top. And so what happens is if you put in something into your test tube and then set it in this container, it will actually separate. The heavier things will go to the bottom, the lighter things will go to the top. The larger that acceleration, the faster that separation occurs for you. So that is our example of what is rotational motion, how do we get between it and linear, and then an example of doing one with our centrifuge here.